All right, good morning, everyone. Welcome to the Minnesota Stormwater Seminar Series. My name is John Bilotta, and I'm pleased to be your host this morning. The seminar series is brought to you by the University of Minnesota, including our partners here at St. Anthony Falls Laboratory, the University of Minnesota Water Resources Center. And the seminar series is funded in part and jointly with the Water Resources Center, the Minnesota Stormwater Research Council, with generous funding from our council partners, including Land and Legacy Amendment from Minnesota. Thank you again to all our partners here at St. Anthony Falls Lab for hosting us today. First, a few logistics for our seminar today. For those of you in the room with us, we will be taking questions. I will have to pass the microphone to you, so just raise your hand at the end of our seminar. For those of you online, we will take questions using the Q&A panel within Zoom, so please post your questions within that. And for those of you online, you may also upvote those. If you have any technical questions, please put those in the Zoom function. Also, for those of you in the room, we would appreciate if you sign in. There's a sign-up list, I think, over at the table there, or Andy will pass that around. So please do that for our record attendance. Let's see, other logistics. So we are also pleased that our Stormwater Seminar Series will continue throughout the calendar year 2024. We have a number of upcoming presentations. Those are all available online. Our next seminar will be February 22nd. I believe that's going to feature manufactured treatment devices. Yep, Seth Brown. And so please look at our website for all those details. We will launch more information about the February seminar after today's seminar, and you can see all the upcoming seminars for the remainder, at least for the next 6 months, posted there. As a reminder, all of our seminar series are recorded and available for your viewing possibilities at any time during your day and your evening. And so those are all available on our website and the SAFL YouTube channel. So please do access those at your convenience. So with that, we are going to move on to this month's keynote presentation, which is on capturing and quantifying coarse organic matter in urban stormwater. We will start with a keynote presentation by our invited speaker, followed by a panel discussion. We'll have a short minute in between those. And again, please do insert your questions for those of you online as we go. So, coarse organic matter, what is it? Is it in stormwater? To what extent? What is coarse organic matter? And I'm sure our keynote presenter will talk more about this today, including what is large organic solids or gross solids, including fine and coarse sand, gravel, trash, and other organic materials at a certain size, which I'm sure he will talk about today. Our keynote presenter today is Dr. John Chapman, an associate research professor for the University of Minnesota Department of Bioproducts and Biosystems Engineering. He is also the director of the Erosion in Stormwater Management Certification Program here at the University of Minnesota. He is a registered engineer in both Minnesota and Colorado, and he brings a large depth and breadth of experience and expertise to us today. It's my pleasure to welcome Dr. Chapman to give his keynote presentation today. Welcome, John.
Thank you. Thank you for allowing me to speak here today. I'm excited to share this research that so many of my colleagues and myself have been working on. Our goal is to really characterize the gross solids and the coarse organic matter in stormwater and understand the phosphorus associated with it. So as was just said, the largest particles are really what we're looking at, the largest ones that stormwater has to offer. And this gross solids term is used to describe that those large solids. Gross is a double meaning, I guess, and it probably applies here as well. Another term is coarse organic matter, which is the largest organic solids. So the difference between those two terms, if we get into the jargon a little bit, is really just the gross solids includes inorganic and organic stuff of large size, where the coarse organic matter is just the organic materials. But I'll use them a little bit interchangeably. We looked at both of them, and I'm really getting into the jargon here. So let's move on to some pictures. Let me just start off by saying I do not hate trees. After these next 40 minutes, you may think that I feel trees are evil, but they're not. They haven't done anything wrong, but it is important that we understand them, understand their contributions to stormwater and our water resources. That said, trees have leaves and pollen and seed pods and all this stuff that goes into that coarse organic matter and gross solids. And when you include the trash and the sand, then we get the full gross solids picture here. And yes, we do also have this trash. And for this study, we did weigh it and measure it, but we didn't do much else with it. But this is pretty obvious, I think, to anybody who has walked by a storm drain inlet in the fall that this stuff is there. And although obvious, I feel we really haven't done much as far as research on it until recently. And I think examples of this are how sampling procedures that we have for maybe a grab sample with a bottle, those procedures have us avoiding any gross floatables, large pieces in water. So if you take your sample bottle and plunge it down to fill it, you're intentionally avoiding any leaves and things like that. When we have automated samplers, the tube is a small diameter, and so it excludes large material from entering the sample. And a lot of times, those will even be screened to prevent clogging. And so we're again intentionally kind of biasing our sample to avoid these coarse, large particles. And then even in the lab, if those sample bottles do have a large, floating leaf or something in them, a lot of times that might be screened off and not included in the rest of the analysis. So this is all things that are kind of biased, it's ignored almost in our procedures. And why do we do that? I think it's because these gross solids are highly variable, and it can complicate things. And so they're there. We can accept that. But do they matter? I think that's what we tried to look at in a little bit more detail. And also to think about the variability and the impact. And maintenance can help us out with this, right? If we see something like this, there's potentially a maintenance crew that's going to collect that and remove it. Before they were doing that, though, there is flow coming through the leaves, potentially leaching out any nutrients or contaminants and things associated with that. So it is significant, I think, and that's what I'm going to try to convince you of. And the maintenance, I can stand here for a minute and talk about maintenance on if all the maintenance budgets for the cities and the transportation departments across the state were doubled, I still don't think it would be enough money to really do all the maintenance that's needed. So this is an issue that has to be addressed. And I know maintenance isn't sexy. I know my car, I'd rather buy a new car than put tires on my old car and do an oil change on my old car. So it's a tough sell sometimes, but it is really important. So let me stop talking about car maintenance here and get on to the gross solids. So the first question we had on this is, how do we even sample this material reasonably? And so the group of us really focused in on this, and we came up with several ideas. We tried several things. I'm going to explain a few of these, and then we'll talk about some of the data, and we're going to wrap up with the potential modeling that can be done with this to predict, how much of these gross solids and nutrient loads we have in our environment. So, total storm capture. Back in 2008, there was a paper by Kahanian who really emphasized the problems with automated samplers and potentially biasing our data coming to us. And so from that, in 2018, I had a project and we really tried to do a full storm capture. And we selected smaller basins that terminated in a single pipe. And then we would build a basin like this, a temporary basin, where we'd collect every drop of water that came out of that storm. And then we would also analyze everything in there. And that total storm capture, we hoped, would give us a better insight without any bias. And so building on that for this study, I'll call this the Total Capture 2.0. Instead of having to build these basins everywhere, we were using these 55-gallon barrels. And we could chain together as many barrels as we need. The first barrel would have a filter bag in it to help screen out and make sure that the coarse solids were captured. The last barrel, we would have a discharge weir and a standpipe. And if we did have overflow, we would be able to monitor how much was coming out and take grab samples and look at TSS values of that material exiting. So we could be fairly reasonable that we had a full capture of it. We did not electronically automate this, and that would have been nice. It would have kept us from having to stand in the rain, but I'd say that would be the next step. And this generally worked. It does have some challenges. We are limited by the location. We have to choose a pipe network that is fairly simple. And even with that, we often had to put a pipe block in someplace or try to modify that a little bit to make sure that our capture zone didn't have any other influences from other pipes or things. And we're also at the mercy of our storm events that nature gives to us. So we did this at several sites for this research using the barrels. We didn't get a lot of rain in 2021 and 2022, so our data sets are kind of limited. But we also used some other techniques, and I'll talk about those more in a minute. But while we were doing total capture, we also tried to run both bottle grabs and automated samplers as a comparison, so we could look at these. A couple other sites that we used for total capture that we evaluated were the Mississippi Water Management Organization has what they call their St. Anthony Regional Treatment Facility, or SART, and that is a large underground chamber. And so we looked at the records, we looked at their automated sampler data, and took some measurements and some samples to evaluate how well this could be used to characterize gross solids. This is what the inside of the large vault looks like there. We did have to go down in to get our samples. This is one of the students, Amanda, going down to grab some samples. And I just love the excitement of sampling that you have. And I wish that excitement would just persist always, but sometimes it fades. So to look at just some basic grain size distributions of this material, when we get total capture, what we find is a lot of our samples are much coarser. On this plot, I have a line with, let's see here, if I push this button. This line is one of the NURP, the Nationwide Urban Runoff Program grain size distributions, and you see it's very fine compared to all of these other ones that we collected in this study and some other data that I had with the total capture. So much coarser. And I think that's one thing to think about is, yes, our sample collection can do a better job getting this more reasonable distribution that we see in the environment. I'm going to skip over that one real quick. And then the comparisons of these methods. I think this was also really interesting as far as how we might be biasing our samples. And so this is another site that we used. This was the MWMO parking lot sump. We evaluated if this could be used for a total capture. And I have two plots at the bottom here. And these basically have time across the bottom And then we have a TSS value on the vertical axis. The orange line is the automated sampler data. And you see that is somewhat variable. It peaks and comes down. And then we also have a blue dot here that is a grab sample. And then our total capture effort would be the gray dot here. And so some initial observations from this, our automated samplers, we were pulling samples every 6 minutes. And with that, you still see a pretty high variability and some differences between the grab capture and the automated sampler data. What's interesting here is we had an hour after we stopped, before we could even wrap everything up, it started raining again, and we collected more data, and we kind of have a second first flush with our automated sampler. We still have variability in the grab sample, and then our total capture, because we had those 2 storms back to back, and we weren't using our barrel method. We did have some contamination between the storms, so our data is a little bit fuzzy there. But I think the message is that I want to share is that this is very time sensitive. And if you pull a sample at the wrong time, it might highly bias what your understanding is of that storm event. This is another site where we're seeing the same thing. This was using the barrel technique, and we have the automated sampler giving us some variability, the grabs showing us different values, and then the total storm capture potentially giving us sort of an average here. We did have some data problems on this one, so there's a potential higher value that could have happened there. But anyways, having a technique that is less biased is really going to be important, in that the sampling is time sensitive. I think we really have to understand both of those. The third kind of initial conclusion on this part of the presentation is just that the sediment is likely much coarser than some of the historical data that we see published in the past. We tried to expand this into more samples, understanding that time is so important, that the total capture 2.0 barrel system wasn't going to be practical for us to use on a number of sites for 2 years constantly. So we came up with another sampling technique that we call it the net sampler. And this tries to take advantage of existing stormwater capture locations, like a catch basin or a rain garden or something at the terminus of a smaller watershed. And we would add a net that we would use to capture these gross solids on a 2-week interval. So that is kind of the other sampling technique that we used. So this is an example of a rain garden that we went to. This is Aaron and Lucy out installing one of our systems. So we would use silt fence to back this up a little bit at some locations. We had so much material, it wouldn't all fit into our fruit tree bug net, bungeed onto a barrel. That was the highly technical system we were using, a bucket. Or in this case, we found what worked well is just a office trash can with the bottom cut off, using the rim of that. So those are a couple of systems that we were using to collect the material. And then the hard work is getting out there every 2 weeks, where this is a before and after picture of one of the sites where we collect, and you notice the large bag, trash bag there, full of our sample. That was basically a 2-week mass that we'd have off of this. And we have other sites. This one also demonstrates some of the complexities that we have with these samples. When you have additional leaf material in the street, how far do you go? How far do you collect? So we had procedures where we had an apron that we would clear, and anything outside of that apron, we would have to wait 2 weeks for that to migrate in, just to give us some consistency in our sampling techniques. This allowed us to do 13 sites around the St. Paul area. We chose different sites based on their canopy cover from 0 to 70% canopy cover. We had a few parking lots. Most of them were residential. I should actually point out these ones in green, these residential ones, were kind of the problem children for us. I'll mention that more in a little bit. The basins we looked at, the different small watersheds, had existing capture locations, and you can see here some of the structures that we modified. These concrete turret structures have a filter screen in them that we removed, replaced that with a piece of board and our net. This one, again, we replaced the screen with a board and our net, and then you saw our other system here that we were using. Every 2 weeks, we'd go out, grab the samples, determine the mass, the dry mass. We'd do moisture, and then the organic matter and total phosphorus on a lot of samples. We weren't able to do total phosphorus on every sample. We just tried to do a lot of them for representation. And from that, I'll show you a couple of these plots. There's a lot going on here. We have the different bars. So this is all of our 13 sites. And the different bars represent the different seasons. So we have a winter, spring, summer, and fall season, essentially. And then the dry mass, cumulative dry mass, is the height of the bar. Across the top, the blue dots just indicate the higher canopy cover areas. These are the 50% canopy cover, or the parking lot 0% canopy cover. The bottom line here, there's a lot going on, but average, we had about 208 kilograms per hectare of dry mass material on average. In 2022, we can look at a similar plot. The average number is 252 kilograms per hectare. So it's a lot of material. And even from 1 year to the next, we saw, what is that, about a 13% difference between these 2 years. We can see the trends, as you saw, the more matter was showing up where we had higher canopy values. And so we can look at some of these regressions and putting it against, putting that dry mass value against the canopy fraction over the street tended to give us the best regression values. And the brown dots here, the orange-brown dots, provide us with a pretty good regression. The two blue triangles are the ones that are kind of the problem children. That location, they were good sites, but every time we'd visit them, it seemed like we'd have something curious going on. The leaves seemed like they had been swept, or there was construction going on, and it seemed like a sweeper had come through. And so we just had a lot of questions on how good the data was at those two locations. And the fact that they're outliers from our trend doesn't surprise us that much, given some of our field notes on stuff that was going on there. Looking at the total amount at each of the sites and thinking about just the percentage in these different seasons might give us some insight. You see the residential sites are actually pretty even from the winter and the early spring, kind of the mature season. And then the fall is a lower number. And we have that trend also in the parking lots, more or less. And so it's pretty even as far as when these and when this material is coming to us. I think what's not apparent when we average this out is that the difference between that dormant and early phase, the winter samples tended to be really concentrated in one sample right when all the snow melts. Basically, all the leaves blowing around or freezing into the snowbanks, gathering up in those frozen snow piles. And in the spring, when you get those first melt days and everything starts washing out, we'd pull a sample and it was obvious that the material had been there for, the last several months, decaying kind of in the snow. And then once we had that sample and we cleared that, the next sample, or maybe even a couple days later, we might get a rain event, and all the material in our samplers now are the fruit, the seed pods, buds, and that sort of material, and it's very different. And so I think that, difference from the dormant season, seeing that that value doesn't represent the intensive pulse of that hitting our catch basin collector sites. The other one, the parking lot dormant value being higher, I think can be explained a little bit from this data that we have. So this is a plot of the organic versus the inorganic mass of all the samples. So we have over here on the residential site, the kind of rate accumulation. This is the Julian day. So if you think throughout the year, we have an accumulation rate of the organic mass climbing here, and the inorganic mass is this lower line. But on the parking lots, they're reversed. We have more inorganic mass and less organic mass. And so I think the parking lots tend to have more grit and sand, especially coming off of the winter months. And so we'd see that in our data as well, that as far as those gross solids, the parking lots were picking up more of that. The phosphorus was another piece to this. So our phosphorus data, when you look at this, you see a lot of scatter. Professor Grace Wilson did a great job doing a piecewise linear regression on this, and it makes it usable. We can infer some things from this, but if we look at some of the other research, I think it'll help us understand this a little bit better. There was a paper just recently by Sui et al. In 2023 looking at some tree species in Australia. And they had estimated that in their data, there was about this 0.0005 grams of phosphorus per grams of dry mass was a residual phosphorus, and that would end up about here on our data. And then between this 0.0025 to maybe up to 0.0074 grams, depending on the species, you would have bioavailable phosphorus, which would be orthophosphate or metabolite phosphate, lipid phosphate, nucleic acid phosphate. And so that kind of, you see those ranges in the variability between different tree species kind of fits into our data. If we had parsed this out by individual species, we may see this clean up a little bit. Another study by Hill and her colleagues in 2022 also looked at the different, leaf material, whether it was the fruit versus like the pollen versus the leaves. And the fruit material was, the blossoms were potentially 2 to 7 times higher than the leaf material. So again, if we think of our leaves being more of this residual material at 0.005, wherever my pointer is here. Anyways, 0.0005, that would go up to about 0.0035, including some of that more phosphorus intensive material on the trees. So it kind of fits within our data, given the species variation and the date variation, that we're going to see this sort of scatter. But we can take those numbers that we did come up with into our piecewise linear regression and make a plot like this that gives us the total phosphorus against the tree canopy fraction over the street. And that allows us to have a decent trend that we could use for modeling and prediction and some of these things. And again, the two blue triangles are our problem children on the the sites where it seemed like there was some activity that we just couldn't nail down what was going on there. So the big message that I want to leave you on this part is that the dry mass that's coming off from these trees, leaves, the gross solids, is somewhere in the range of 200 to 250 kilograms per hectare per year. And the phosphorus that we're seeing in our samples, the contributions from this, is probably being missed by the ISCO samplers and automated samplers and other equipment that's out there, which could result in maybe a phosphorus loading in our watersheds that's maybe 14 or 140% larger than what our ISCO data is telling us now, just because of this material is still sitting there. It's not getting into those water samples. It's still waiting, so to speak, to be transported down to our water resources. So the last thing I'm going to touch on in the big picture here is modeling. What can we do with this? And for this, we used the P8 model, which is a free model, readily available. And what I like about it is we can kind of open up the hood and tinker with the bits inside. And it's not a black box that's locked up. And so we took our data that we had and plugged it in to see what we could do. One piece that was missing so far, I haven't mentioned, is Aaron Peach, for his master's thesis, he looked at the settling rates of this material. So he took a camera and several leaves and seeds and measured the settling velocities of these, and he was able to work that in with the some of the traditional kind of Ferguson and Church type settling equations by adjusting the coefficients and come up with a pretty good relationship. And so that was instrumental to allow us to get into these P8 files and start to modify them to have basically a gross solids pollutant file. And in P8, like I said, it's not locked, so we can tinker with this. And there's a couple of files that you never want to touch when you do a P8 model, and then that's the pollutant characterization files. And of course, those are the ones that I ripped apart and changed. Okay. So the one on the left was working with our straight kind of accumulation rate values that we had. We plugged those in, the settling rates. And then I ran that through the 2021 data, or I used the 2021 accumulation rates, and I compared it to the 2021 data, and I fine-tuned it a little bit. And so we came up with other files that were calibrated to that 2021 data. And it's not a great regression for this sort of a model verification study. If you look at our R squared value is around 0.8. But that's not too bad. And then the problem was when we applied this, I tried to use those values to model the 2022 year and see how close we could get. And what we had was a shift. Our trend is not on a one-to-one relationship. So we are missing about 20% of the mass that we did observe in 2022. But if you remember earlier, I said that our total solids coming out of these 2 years were different by about 13%. So I think the problem that we have is that this P8 model does not have any mechanism to account for biomass growth. There's no growing days or precipitation impact to leaf growth and these sorts of variables. So I think while this is potential, we can use these numbers to get an understanding. It's not going to be very accurate until we come up with a different model that has that biomass growth component to it to allow us to better fine-tune that. And so that's in a nutshell what we have. But I want to leave you with this last piece, and this is hot off the presses. So Natalie Nervaez it was a honors student undergraduate who was working with us, and she wanted to do her thesis with some of our data. And I think this is really interesting because she took two of our sites, the RG2 and RG6 locations. And bless her heart, she went through and identified every species of leaf in those samples. And then at the sites, she identified all of the possible trees that could have produced those leaves and mapped them basically. So we have these plots, and the lines indicate the closest trees for those, associated species. And what we see on this, and she also looked at the windrows data from the airports to look for trends. And so we have these relationships, the red lines, and I'm not getting this pointer to work real great, but there we go. So we do have some lines here where she was plotting the mass of the different trees in basically their compass direction, and how that relates to this preferential wind pattern that regionally we have mainly winds from the northwest and southeast occurring depending on the time of year. And on this one, we had a couple of outliers, which interestingly enough follow the street corridor, which this collection point was along the street. So we seem to have an influence, maybe a local wind pattern caused by that street. When we plot up some of this data, these lower plots have the distance that the trees were from our site and the dry mass collected. The orange dots are the trees within the hydrologic watershed boundary. The blue dots are the ones outside of the hydrologic watershed boundary. And these top plots are plotted, this bottom line is the compass direction from 0 to 360 degrees against dry mass. And these shaded bands are those two preferential wind directions that we saw in the windrows plots. And you see some of these clusters of trees are in those kind of windrows or preferential wind areas. So the two big messages here are this material is coming from outside of the hydrologic watershed, potentially influenced by wind more than other things. And so the big conclusion that I have is all of time and space needs to be considered when we think about gross solids. I can narrow this down a little bit. So when we think about gross solids, we really have to account for these in our stormwater. It's important. I think it does have an impact. We need sampling techniques that can really capture the gross solids. Some of the existing techniques aren't doing a very good job at that. The fate and transport of phosphorus does need to consider gross solids, and that may have variability due to growing conditions, wind conditions, and may not even be normalized by watershed boundaries, which is kind of a headache. And we can adapt, I think, our existing models with some limitations, but new models that have a kind of a growth mechanism to them might be needed in the future. And then I do think that accounting for all of this, even these numbers that I have here, can really help us think about maintenance and when we need to get out and how much it's going to cost to collect some of this material to get it out of our out of our infrastructure. But it can help us design better stormwater management control measures in the future. And with that, I just want to recognize our funding sources. We had funding provided by the Minnesota Stormwater Research Council and the University of Minnesota Water Resources Center, and all of their partners listed here in the text. And of course, the Clean Water, Land, and Legacy funding is a major part of this. I also want to recognize the amazing team of students and researchers that we had and partners for sharing all the data with us. So thank you.
Great. We'll take some time for questions to Dr. Chapman, either from in the room here, I'll pass the mic, or online, we'll alternate. So questions for our presenter today.
Hi, John. I'm John Gulliver from the University of Minnesota. I had a question about your total mass charts, and you had the total mass was greatest during the dormant phase. I presume that's winter, and smallest in the senescent phase, which I believe is fall. I would think it would be the opposite of that. And can you explain why?
Yeah, so that's a great question, and I also think about that a little bit when I see it. And I believe what we're seeing is in the senescent phase, the volume might be larger, but the mass might be a little bit less. So I think the leaves, when they're dried out and lighter, it might be that we have a heavier mass from the different, seed pods and various things like that are falling earlier in the year. And those were a total mass. So that does also include the gross solids, the sands, and the other components. So those also get kind of mixed in there with those plots when we average it down that way. Just like in the parking lots, I think that's why we had that stronger influence in the winter months, was from potentially the grit material in the parking lot.
Thank you.
We have a question online, and the question is, several studies on leaf collection and street sweeping in Wisconsin municipalities by Bill Selbig et al. Have indicated that large amounts of bioavailable P are lost from large particulates as the nutrient, quote unquote, T in the first flush is washed out during the storm. How did you account for the water washing phosphorus and nutrients out of your collection bags?
So that is an excellent question. And I think we did not try to investigate that specifically. But what we were thinking is, by collecting every 2 weeks, or we would even do it quicker if a bag were at risk of being lost or overloaded. We were hoping to get out fast enough to get kind of a baseline phosphorus remaining there. I understand that even a leaf on a tree, as a raindrop encounters it, is going to pick up some phosphorus from it. And so there's other studies looking at that. And I think we were focused more on how much is left after that leaching has occurred. And in that material that is leached out should be showing up in an ISCO sampler or an automated sampler or some other sampling spot. And so we were looking more at the material that's being missed from that. So I think that's a great question, and it's really just out of the scope of what we were looking at specifically. But it definitely ties into the big picture of what we're trying to figure out.
So I'm Randy Neprash from the Minnesota Cities Stormwater Coalition. I'm curious about the lessons or take-home messages for the community in general. One, perhaps the biggest, most general one, is this is a lot of material. And among other things, it's a significant nutrient content in the material. So more work to understand this and quantify it better is worthwhile and should be a higher priority. I'm curious about some of the details. So leaves are a big deal. Are seeds and flowers an equally big deal? Hardly anybody talks about those. Seems as though this whole snowmelt, the idea of leaf decomposition in the snow during the winter, and then this gigantic flush during snowmelt also seems like a big deal. The the last question, I'm looking for confirmation, I guess.
Yes.
You have to do more than head nods for the web audience, I think. The last piece, though, is something that you mentioned, but it sounded like you didn't really look at carefully. But EPA and the regulators are really concerned about trash in general, and then plastics in particular. And did you find those types of materials in sufficient quantity that those also should be prioritized for additional research?
So Randy, thank you. You make some excellent statements, and I agree with all of that. And I think the data that we have shown here definitely suggests that there is a material coming to coming out of our watersheds throughout the year, even in the winter, and it all has to be considered in the seed pods, and those things are just potentially as phosphorus laden, if not more phosphorus laden than the leaves. And the timing of how to collect all of this is a challenge. And I think we definitely need this data that includes the winter, capture. And that's where our net collectors allowing us to do full year capture were really important. As far as the trash, we had more trash in the parking lots. We had one of our parking lots is near a football stadium, and so we did see some odd trash issues showing up from tailgating. We actually had to dispose of one of our samples because it seemed like it was a grease trap scenario where somebody had disposed of something, illicit discharge of some sort. In the residential area, we did not see a lot of trash. We did see more trash during the state fair time periods. I think we had higher traffic loads, and obviously that trash was corn dog sticks and wrappers and things associated with that activity. So we did see trends that we could pin on different activities. I believe that trash is potentially something that could be studied and managed based on more of our social behavior. Like I'm saying, a lot of the stuff that we saw anecdotally says that it's related to our own behaviors. And so a targeted trash collection at specific times could be very successful.
Andy, we have one more question online.
Sure. Yes. We have another question online, and this one is, during automated sampling, how did you get around the sample bias from attaching a sample line to the bottom of a pipe or stormwater structure where large particulates tend to concentrate? This may account for your difference in TSS levels between grab samples and automated samples.
Yes, that is an excellent question. The inherent bias that's generated with sample location within the stream flow. We did not try to correct for it. We tried to use a kind of typical automated sampler scenario to represent what might be happening with other automated sampler data collected historically. And I know there has been some work on different orifice inlet ports on those samplers that could correct for that, and we did not attempt to use any of that for this. But that's an excellent question.
Another question from the room here.
Larry Baker, I'm a free agent now. Research professor emeritus. On the winter thing, I think as we move upstream a little bit to thinking about exactly where things are coming from, the winter issue, I think, is a very, very big one. There was an excellent study done by Brian Horgan on turf runoff under very controlled conditions, probably 10 years ago now, or 8 years ago. And they measured runoff all throughout the year, including the winter. They used melted warm buckets and stuff like that. And Brian tells me that they had more runoff during winter melt events under these we get these 40-degree days in February and things like that. They were getting more runoff phosphorus loading coming off these plots in the winter under snow cover than they were in the rest of the year on some of the plots. So things are happening under the snow. And especially as we move toward more warmer winters, we're going to probably see more of that. When it's 20 below zero, is probably not when you're generating runoff. But if you back that out, where does it come from? Well, we're told to mulch our lawns on the last cut. Most people are even mulch the leaves, if they're not too thick. And we often fertilize in the fall. If you do one fertilization, it's usually in the fall. Well, all those things and probably a few others. And you have dog poop accumulating sometimes in the winter in people's backyards and stuff. So there's this really large potential here, and it's probably something we should start thinking about a little bit more. And I'd say in the agricultural realm, that's been shown that a large part of the phosphorus loads come very early, half of the loading before June. And Jacques Finlay has shown that in one site in Capital Region that there's a very large amount of nutrients coming off prior to anything growing. So we need to reorient or expand our thinking a little bit on that issue.
Excellent comments. I agree that having a monitoring system that includes the winter is important, critical. Absolutely.
We could probably take one last question in the room, and then we are going to take a short break before our panel discussion. So, and we'll get to some other questions online during the panel too.
Thanks, John. Mike Trojan kind of retired. I'm curious about the first flush. How often did you see a first flush? And then in that one event where you showed a second first flush, which is kind of an oxymoron, what do you think caused that?
I would say pretty much all of our data for the automated sampler suggested that there was a first flush, and at the site where we had two of them, I have not dug into the precipitation on that, but the rain that day, I think it was probably an intensity thing, that maybe the second storm event was more intensive and would have generated more material coming off of the watershed at that point. So, but I haven't dug into that carefully. Yeah, but that's what I think is going on with those. Excellent.
Well, great. I know we have a lot more questions and a lot more questions online. We are going to take a short break before we feature John along with our panelists, but let's give Dr. Chapman a round of applause here. All right. Well, welcome back. We're going to start with our panel discussion on this topic of coarse organic matters. And it's my privilege and honor to introduce our panelists that have joined our keynote presenter today. And so I'll do some introductions of them and start with an initial question to them. So starting on my right, your left, on the far side of our table, our first panelist is DeRusha, who is a water resource specialist at the Washington Conservation District. Aaron, thank you for joining us today. And from your perspective and everything you heard, how do you relate to this topic of what Dr. Chapman talked about with coarse organic matter?
Yeah, thanks for having me in. Appreciate it. Appreciate the introduction there. Yeah, I can relate to it from a couple different ways. At the Conservation District, one of my primary roles is water quality monitoring. We do large number of sites for our Watershed District partners and cities in some cases. Last year, we had a really big year for monitoring. We had 50-ish sites that were located on streams. Probably 35 of those had ISCO automated samplers, like John mentioned, and exactly 0 of them account for coarse organic matter currently. So that's a huge load that we're potentially missing, because we do take that monitoring data and synthesize it into a report for some of those watershed district partners, which usually include annual loads, as you might imagine. Another, role that I have there is coordinating our construction, stormwater, erosion, sediment control, inspection services for our partners. We do that for a couple of cities and watershed districts. So I could see applications where this would really apply to that as well, as far as controlling organic matter going into inlet protections during active construction. I've been out on construction sites where it hasn't rained in a month, and their inlet protection devices are completely packed with leaves and coarse organics, which obviously are not going to do a good job capturing a flush if it were to come through, and containing the sediment if they have track out issues on pavement and that sort of thing. And then I'll just mention really quick, our office does have a large B&P inspection and maintenance program as well. So I'm sure they would be very interested in timing for those, and what kind of organics they should be removing and when to remove them. And then we also did a GIS desktop analysis for the enhanced street sweeping with the Lower St. Croix Watershed Partnership, which I'm sure Paul is going to talk about next. So.
Well, thank you, Aaron. There's quite a few comments there we can pick apart, hopefully, in some follow-up questions. But let me introduce you to another panelist, Paula Kalinosky, who is a hydrologist with the Stormwater Research Engineering and Outreach Group with our Minnesota Pollution Control Agency. Welcome, Paula. And lots of experience also with coarse organic matter and organic matter. From your perspective and what you heard from John this morning, some comments. Yeah.
Sorry. Is that terrible? You just got introduced. Aaron referred to my previous life. My graduate thesis when I was a master's student at BBE was on a street sweeping project, which a number of people are probably familiar with the outgrowths of that. I see a lot of people in the audience here who were connected in some way. But I work at MPCA now, and I'm the coordinator for the Stormwater Manual. So obviously there's a lot of content there that we provide for stormwater managers, practitioners, et cetera. And right now I'm thinking of a number of things that we'll have to consider, like just stormwater characterization in general at the top level, but we have guidance on pretreatment, best management practices, source control practices, both residential and municipal. There's guidance on all of these topics within the Stormwater Manual, and this coarse organic matter component being much bigger than perhaps we thought before is potentially going to influence, or we're going to need to rethink some of that guidance and refocus on our treatment train.
Thank you, Paula. And our next panelist is Sarah Wein, who is the monitoring coordinator for the Capital Region Watershed District, and certainly a lot of experience with dealing with monitoring aspects of what we heard about. So comments from you, Sarah, about what you heard this morning and implications to our work.
Well, thank you. I'm very happy to be here today. So Capital Region, that were some of the sites that you just saw in Dr. Chapman's presentation, were located there. So you saw a couple pictures from in our district. We're highly urban. I had a colleague query our BMP database, and we have over 1,500 stormwater infrastructure BMPs in a 41 square mile radius of or 41 square mile area of our watershed. So that means we are either managing, regulating, permitting, educating about, monitoring all of those various pieces. We have a hand in a lot of those, in almost every single one of those in our database. And so we're very interested in how coarse organic matter is going to impact the integrity of our stormwater infrastructure. So coming from kind of two major perspectives, we, as the monitoring coordinator, I'm responsible for, literally my job title is very specific. I help coordinate the monitoring that we do as a watershed district to answer a lot of the questions that our project managers then would have in terms of how could that be impacting what are our phosphorus loads, what are our TSS loads, what are we looking at here? And the two main questions we're trying to answer are, what are the performance of our stormwater infrastructure BMPs, and how can we most efficiently and effectively organize maintenance for those BMPs. The ones that CRWD manages, we have maintenance plans for those, and our data has really shown how important that is to have the monitoring data to back up how frequently you maintain a lot of those to protect the integrity of the system. So really unique. I've been the person jumping into a sumped catch basin for this type of sampling technique. So when you said gross solids, I was so glad you had made that joke already, because that's what we described. We called it, you surf down on a little board into the catch basin to compact all the material. And we've done some really interesting research. And another thing that you ended with, the all of time and space should be considered. That's sometimes how you feel in monitoring, that you could monitor the heck out of anything. And it's really trying to figure out, what do we have the time and money to do to get the most efficient and effective data set to provide information for the people that need it to impact stormwater design for better design systems, because it's very important. So that's kind of the perspective we're coming from in CRWD.
Great. Well, thank you, Sarah. And I won't ask John to comment on his own presentation, but Sarah went right into one of my first questions for the panelists and challenges that you encountered. John started with the challenges and problems about how to even monitor the coarse organic matter. And Sarah, you gave a perfect lead into some of the problems and challenges and observations you made. Maybe Aaron, on the opposite end of the table, can you concur, or what have you seen with these challenges of even looking at and monitoring the coarse organic matter?
I think probably one of the biggest issues is the variability in size between sites. You know, we have some that are BMPs, like Sarah mentioned, where it's very concentrated. You could foreseeably put barrels or nets or something on the outlet of that structure. And then there's others where it's an 8.5-foot pipe that takes half of the city's drainage at some point, and it goes from a trickle that's 1/10 of a foot deep to 4 feet deep and 250 CFS in the matter of 15 minutes. So how do you account for coarse organic matter in a situation like that? Can you model it? Can you not model it based on smaller practices? That's all, something we'd be really interested in, I think.
So you have not tried to do the butterfly net like John did on those situations, huh?
Yeah, pterodactyl. Yeah.
All right. So hopefully you all can observe we have a diverse set of panelist members to tackle and address and have a conversation about this topic. And so let's take some questions from all of you, both in person and online. So one from in the room here to our panelists. Dr. Baker.
Yeah, we're doing an awful lot of monitoring, and I'm wondering sometimes how much that's really worth. We have this illusion that we treat it like an engineering problem, where we have a total daily maximum load and we have to reach that, and ideally within some statistical limits for each of those structural control measures. Is it time that we back up to the 30,000 foot level and maybe ask a little bit different question? Are the receiving waters that we're going into directly improving? Are nutrient concentrations going down? And I would suggest that they probably are changing, and they may be changing partly because of structural BMPs, but partially because other things are happening. We have no phosphorus fertilizer now. We changed the way we do construction over the past 20 years or so. A lot of things are happening, and I think that there's probably as much happening in the watershed that's changing the downstream water quality as is done by the structural BMPs. And so what I'm suggesting is kind of an adaptive is it time to move to an adaptive management approach, especially with the use of artificial intelligence and all that. I just want to get a feedback on that. But before that, let me make one point. The number of lakes, nutrient impaired lakes in Minnesota that have been restored, have been delisted. So they now meet the requirements they didn't have. The ones that were listed are now delisted. Of the ones that have restoration measures associated with them as the cause of this, it's 6%. We have not done much to improve the nutrient status of lakes in terms of, if you use listing and delisting as a performance metric. And just any comments on that?
Maybe the first part of the comment and question, maybe we can back up to that with the challenges that you've expressed and John expressed. Should we back up and look at monitoring or something at a different level? 30,000. Are we approaching this and looking at this incorrect, or it could be in a different way? Dr. Chapman.
I think I can lead off with just a comment on that. I like the idea of monitoring the end spot for how it's been improving over the years. And I think my challenge with that is the historical data that we have. Does it fully capture the variability within those water resources? If we have, maybe 10 years of data or 20 years of data, that's great. But was it collected once a quarter or once a year? And does that really capture the nutrient loadings within that water resource in the full kind of, is it also biased? So is that going to be a challenge to us to do management by looking at that end receiving water without understanding the bias in that value that we assign to it? So I think that's my first comment. I don't know if others have other thoughts on it.
Well, Larry, since you asked a big one, I'll put a big answer out there, big picture answer. So I tend to think of, the problem is the streets. I always say this. We want impervious surfaces. You think about how all of these streets are connected to our water bodies. It's like a series of arteries or something. They get to feed off of areas that they wouldn't perhaps in a natural setting be receiving, inputs and pollutants from. And we're not going to get rid of streets, but kind of what we're doing is by having the streets there is all this material that comes down the street and into the sewers and everything. We end up having to manage that. And it's like we're just taking piles of stuff and trying to keep it back where it started. And so it just goes back to that source control question, because really that's what we're doing in the end. It's kind of a simple concept, but you asked a big question, so I'm going to put that out there.
Anyone else from the panel?
I think I'll just echo back what you're saying, that it's really hard to look at lakes. Like there's 5 lakes in Capital Region. We more intensively monitor 2 of those 5 lakes, and all of our water eventually makes it to the Mississippi River. So we, Capital Region, don't do any monitoring on the Mississippi River, but our goal in all of these projects is to also just reduce Capital Region's contribution of all of that loading to the Mississippi River. So we know all of those projects are having an impact. I think it's, for us, again, I'm really going to stress that maintenance piece. A lot of the data that we collect really helps us understand how frequently these places have to be maintained, with the knowledge that if you had all the money, I can't remember how you phrased that first part, that if you doubled that budget or something, maybe that wouldn't even have an impact. But I think kind of knowing we do a really good job in our district of maintaining, really helping to keep the integrity of those systems so that they're functioning well, and knowing that they're having reductions. But if you then go down, from the scale of the water, our watershed, to a scale of one of our local lakes, one of our large BMPs that was put in very shortly. It was one of the first major BMP projects that was put in after Capital Region was created. And it's still operational. Everything's still functioning within that large BMP. It consisted of a huge treatment train of different BMPs, from sumped catch basins to sumped manholes to understreet infiltration trenches. Those were one of the first of its kind I believe in Minnesota, for sure in St. Paul. And then a large underground infiltration gallery, and all of that was upstream of a local lake. And could we directly tie monitoring data we're collecting in Como Lake to that one single project in a part of one of the subwatersheds of the lake? I don't know, right? But we know that it's having an impact because we can calculate those performance reductions and know that if that wasn't in the ground, all of that would otherwise be going into the lake. So kind of also from a bigger picture, just knowing, even if we can't directly tie, and we can look at overall water quality trends. And I think they're so multifaceted, right? There's so many pieces that are coming into play when looking at a lake water quality and how is that changing over time.
Well, great. Well, I know we have lots of participants online and have a lot of interesting questions. So let's take a different direction here. One of our online questions.
Yes, we have a question online that actually builds off of what you were just talking about, and I'll take the question, but I'll broaden it a little bit. It came in during John's presentation. The question is, how does the additional gross solids per hectare impact the annual total phosphorus loading? Or again, if we broaden that, thinking about what we're learning about more gross solids in the runoff than what we previously thought, how does that affect all of these assumptions we're making or these other pollutants we might have to deal with?
Mm-hmm.
Are you just jump in or?
Yes.
You had a thought. I'll let you go first and then I'll noodle mine a little more.
Yeah, I mean, I think, John, you mentioned that it was maybe up to 140%. Did I write that down correctly? That could be additional load over the dissolved and particulate?
Yeah, the phosphorus that's still sitting in that gross solid somewhere could be as high as 140% more than what we're measuring or accounting for.
And and that's substantial when you're looking at TMDL reductions and those sorts of things that we aren't accounting for right now. And maybe there's cases that our BMPs are actually doing a really good job and they're potentially not getting credit for nutrient reductions because we don't know how much they're capturing. Or maybe we need to be installing even more in some cases because it is letting through all the coarse organic matter. We're not capturing that, would be my thoughts.
Yeah, and I'm just thinking about characterizing the source area. In the case of a TMDL, we diagnose that at the water body. And so I think we feel pretty solid about those numbers. But and then we assign waste load allocations, but that becomes kind of that's a very difficult thing to do on a lot of different levels. But if our stormwater characterization has missed this piece, it means we need greater reductions, like you said. And I think about, we often model the potential reduction that a BMP is going to, how it's going to perform. And if we don't have that source water characterized properly, if we're not accounting for all that phosphorus, we're just, we're going to overtax that BMP potentially. We wonder why it's underperforming. But I thought about this with street sweeping in particular, because that's a source control BMP, and we've characterized it by looking at what we are recovering. And we also recover material from BMPs and ponds and such. But if that's hasn't really been accounted for in the downstream place where we evaluate the effect of street sweeping, meaning we have an ISCO sampler and we think that have we reduced TSS, have we reduced phosphorus? But if we're missing some of it in that sampling procedure, then we don't really know the effect of street sweeping. Potentially it's a greater impact than what we have thought. And I just want to say regarding TSS, I think we got to rethink the categories that we talk about sediment. I mean, total suspended sediment is what will suspend. There's no TSS on the street when it's dry, right? Technically, there's no TSS on the street. It's not suspended. But yet we reduce TSS by sweeping the street. And I really think we need to start thinking about it in terms of fines and, coarse minerals, coarse organic matter, and target those more specifically with our pretreatment and other BMPs. Yeah.
I'll just comment to the question online and emphasize the fate and transport. The leaf, where is it? Did it stay in somebody's yard? Is it still on a street someplace, or did it wash all the way down into that water resource? And the fact that we don't really know if maintenance picked it up or not, that's the piece of this puzzle that's kind of missing for me. Is if that piece of gross solids is flushing all the way down into the lake, then it's there. It's in the lake, regardless of the form that it's in right now, bioavailable or not. It's phosphorus in that water resource. But did sweeping pick it up or not? And can they pick it up, or is it back in somebody's yard or frozen in a snowbank? That's the questions that I have that make it tough to evaluate. Is it going to impact this water resource or not?
All right, let's take another question from in the room. I think Randy's hand was up first. I'm going to go over here.
So this follows on the comments about maintenance. Not fun, certainly gross. Not hard to fund. We're not doing enough of it. We have BMPs by the thousands where we're collecting these gross solids, and we're not removing them. As I feel confident about this statement, we're not removing them nearly as frequently as we could or should. We have this kind of brilliant model now on street sweeping where we quantified the amount of material, we quantified the nutrient load, we set up a measuring system for regulated cities, and now we provided a crediting system for those regulated cities. And now we're seeing cities, watershed districts picking up on enhanced street sweeping. The feds are willing and eager to fund the acquisition of street sweepers. Should we be taking a similar approach to maintenance in general, to enable the folks doing the maintenance work to quantify the amount of material they're picking up, to calculate or estimate the various loads and types of pollutants, to get credit for the material they pick up? And if we put a system like that in place, could that then motivate better funding for maintenance, somehow get the feds to provide funding support for maintenance, which they don't do at all at the moment? Is that worth doing? And if it is, how do we go about doing it? Easy, nice, simple, easy question.
I can.
I don't have, I think I was just going to snap like, yeah, we should do that. And our monitoring data is showing there's a lot. We're removing this. We should be accounting for this. I don't know how we better use data like this that's being collected to then really use it as a point to prove that would be more justifiable, that money would be really well spent doing something like that.
Yeah, I'll just, I'm the regulator, I guess, at the at the table. I am not as well versed in the MS4 permit as I should be, but it does require that MS4s do maintenance on their BMPs. Providing them with more funding somehow, absolutely. The question that I went to when we started talking about this is, the staffing piece. Obviously, that's a money piece, but then there's the material management, and that is really a big sticking point for most municipalities right now, whether it's street sweepings or the pond dredging. I mean, there's so many ponds out there, and dredged material is a huge issue that we need to deal with. And we have landfills that are full, and we're having trouble just managing our solid waste in general. This material is solid waste. It is regulated by the rules of solid waste, and it has to be either used or disposed of appropriately, depending on the content, what constituents it might have or might not have. And so, one thing we need to do is have more testing of that material so that we can develop some beneficial reuse options at a more local scale, because it's incredibly costly for these MS4s to haul this stuff to a landfill. So, yeah.
I would also mention, I think in some cases there is some credit for street sweeping and those reductions. I mentioned the Lower St. Croix Watershed Partnership, the enhanced street sweeping analysis we did for some of the communities in the GIS. They're developed by Paula and others. Lower St. Croix did offer reimbursement for street sweeping curb miles above and beyond what their standard practices would be, and I think it was like $100 per curb mile up to $5,000. But if they weighed them and calculated those weights that they took off the street, it went up to $125 per curb mile. So there was some good implementation there. So, but maybe not calculating the exact nutrient content.
Yeah, I think there is some data, like some municipalities, and I've looked at some of this where some some cities do track some of their data. But I think the missing piece might be the resources to evaluate it, that they don't, have that study as something that they really budget for. So I think some of the data might be there, but I do like the idea of, and I don't know if I'd want to put a regulatory burden on it, but to track the weights, to have a little bit better, like the hours I think are tracked, the maintenance hours is going to be readily available in most municipalities.
The regulatory credits are much more attractive than regulatory burdens.
Right.
Speaking from the perspective of the city.
Yep. But I think, tying that, mass collected to your credit could be a nice way to collect data and make sure that they get the credit for it.
John, maybe you just started touching on this. I'm going to try to make an attempt to connect multiple research projects that we funded through the council. But your work today looking at coarse organic matters and in underestimating perhaps our contribution, and Randy's question about O&M of specific practices. Well, let's talk about a practice. Sump basins is where I'm going. Your previous work talked about frequency. So if we combine these two studies and looked at operation and maintenance of sump basins, and if we could come up with a contribution in loading reduction, it would support operation maintenance. I'll comment on that. I'm trying to connect these multiple studies.
Sure. Yeah. And that was, so back in 2018, we looked at some municipal records and we did some modeling, and we estimated that if cities did sump cleanouts, a lot of municipalities might do once a year. And if that were increased to twice a year, they would be capturing a lot more of the material. Basically, the sumps will tend to flush out in different storm events, and even increasing to twice a year would vastly improve the capture amount. So I think having that data and being able to evaluate it can give us some great optimization. But we need the data first, and so I think the trick is going to be to get cities to share the data and collect it. And maybe it is a regulatory mechanism that could be used to get that data.
Let's take another question from an online participant. Andy.
Yes, we have a question here that kind of builds on some of this, but maybe it gets into too much detail. But Paula, you had mentioned maybe we need to think about solids differently, right? And so this question is, it's quotes, MPCA, event mean concentration values for TSS are about 75 milligrams per liter. And the person asking the question has always found this to be very low when trying to explain monitored manufactured treatment device performance in the field. So John Chapman's presentation addressed increased loading when accounting for inclusion of the organics. However, has anybody looked at the change in specific gravities when thinking about inorganic versus organic, and how might that affect how we manage these materials?
So Aaron Peach, in our study, when he looked at the settling rate calculations, he tackled the specific gravity. So basically, how dense is your material? And inorganic material, of course, is solid, solid silica, let's just say silica sand. That's pretty easy to characterize. It doesn't change. But when you have organic material with cell walls and vacuoles that might be filled with air, not only is it very light and might float, but those cell walls can break down with saturation. And once they saturate, they tend to sink. And one thing in Aaron's data that I thought was fascinating was the specific gravity started off a little bit, where everything floated, essentially. But after saturation, given enough time, and it was 3 to 5 days or so, depending on the species and the condition, a lot of that material would saturate. And I was just really surprised at how it would saturate to a point just below 1. It just goes below sinking. And I think biologically, have the seeds evolved and this material has evolved to settle out of water. that it doesn't float forever. I think there's probably some species that do, but when we look at all the species in this area, I think it may have, intentionally kind of evolved to break down to just sink, to make sure it gets to the bottom of the lakes and in saturated areas. Any wetland species would have to, almost be designed to or been evolved to sink. So yeah, I think it has to be considered, and it definitely complicates how this material moves through our environment. If it's floating or sinking, and even how that's going to be trapped in our stormwater treatment measures, you're going to have to think about if it's material that's going to be floatable for 3 days, and then after 3 days it'll start to sink, and so our capture system could be designed to account for that, but it takes a little more thought.
Any other comments on settling?
And maybe just from a monitoring perspective, maybe that is a room for some sort of a setup instead of a sieve or a strainer mounted on the bottom of a pipe with intake tubing, some sort of vertically oriented strainer where you could get the bed load stuff in the middle and floatables all together and be able to suck that out without it getting washed out of a pipe or something. But that could be a long ways away still. So.
Yeah, and I'll just say, I think it's come up at a couple of these seminars recently that we need to reemphasize that treatment train, but maybe we need to also build a pre-treatment train, and really, because we tend to design things with a pre-treatment device or a pre-treatment section, a pre-treatment bay, but we may need more than one pre-treatment device to remove all the solids. And I think the coarse organic matter poses a particular issue because given that it takes longer to settle out, right? Because it has to become saturated and then it sinks. Now we're talking about, we're capturing this in water where it's probably going to decompose. We've got dissolved phosphorus being released. And so, we need to think about if we're going to put in a filtration system, where does that need to go? In the treatment train, where's that going to have the most impact? So.
If I may, I know in our advertisement, I think we were going to end at 11:30, but we're going to continue on for about 10 minutes. Time moves a little bit slower here in Minnesota when it's 10 degrees. So if you're able to stay on, please stay with us. We'll take a few more questions in the room and maybe one more online before we end in about 10 minutes. Dr. Gulliver.
I have a couple of questions. First, a few things to address. And one is that, you mentioned TMDLs. Paula mentioned TMDLs and the fact that the monitoring system is underestimating the gross solids. Most of these TMDLs are developed by using P8 or some other type of program. And people might think that P8, that's a well-developed program based upon this great set of data. And then you think, well, what data is it based upon? It's based upon MPDES data, which was taken with monitoring equipment, which had a filter on it. So all the data, all the models are under-predicting the amount of nutrients and suspended solids that are going into our receiving water bodies. So I think that's important point to make. And then it comes to, I come to Randy's question. Well, maybe we can provide a credit for these things. Well, the thing is, we've underestimated the amount of nutrients and total suspended solids coming into our receiving water bodies, and we're going to supply credits for getting rid of it, right? Well, eventually, we're going to have so much credit that we're going to have no requirements whatsoever, right? Because we have more nutrients going in than we think we do. Then we say with our models and with our monitoring, and we provide credits, and suddenly we have nothing, right? But actually, we do have something. So that's something to consider. My question is, how do you guys want to address this? Because I like the idea of credits, but we can't give too many credits.
That's a tough one.
Let's do some first.
Well, I think I'll just lead off and say that if the TMDLs were developed with incomplete data, if a credit were developed and used and it resulted in a hypothetical 0 nutrients and the lake still wasn't improving, I would say that this is justification to reevaluate the TMDL and say that there are more nutrients in there that we need to account for. So I think that could be tied together. Regulatory wise, I don't know if moving the goalpost would be frowned upon.
Yeah, I mean, I guess I have to be careful because just what I'm saying off the cuff and thinking is good is not, necessarily what is a good regulatory framework. But credits are good. They're complicated though, and it's a piece that I think we're learning. It's a new system. It turns out to be more complicated than a lot of us thought. And I think a lot of people who are in TMDL regulation and crediting here and in other states are kind of grappling with, well, what is the best way to do this? Because like Randy said, if you make it too easy, then we miss the mark. But if you make it too difficult, it's just not motivating. You need to provide some incentive, some motivation to do these things. But the crediting process itself and the way to do it is not easy. I had another thought in there that was more specific about this, but I kind of lost it. So we'll see if it comes out again. Not now, it won't.
I think not necessarily on the credit portion. I'm, as part of the monitoring team, this is a realm that I'm not really involved in at our district, but I can speak to the fact that kind of like what you were alluding to with our modeling, that if it's not accounting for that, I think that's maybe an avenue where some of this type of innovative research can really help. Like if we're finding that is the need, hopefully trying to improve our inputs to the models to hopefully have better output.
Yeah, actually, that was kind of what I was thinking about was the modeling piece, because a lot of people are good, well-practiced modelers are aware that NERP particle size distributions might not be accurate to what they're seeing, and they know to calibrate the model to what they've observed, and maybe what we've sampled on the end is biased, and maybe it's not. But there are a lot of different programs and we can make adjustments. I would say the coarse organic matter is a conundrum though, because it's not easy to model in something like P8. It doesn't, because it doesn't follow Stokes' law, doesn't settle out nicely in the same way. And so, as John was saying, maybe there's ways to add that component to our models, but certainly people have been grappling, practitioners have been grappling with how best to represent what we actually are seeing these days as compared to the NERP practice, NERP sampling.
And I guess one final point that I will make is we really think a lot in our monitoring program about how is this data going to be used? What's the benefit in terms of helping to guide our decisions for what we monitor and how? A lot of the monitoring we're now doing for gross solids is simple sediment depth measurements at different points in the year to literally figure out just from a maintenance perspective. So those two main questions, like I talked about, that we're really focused on at Capital Region, what's the performance and how do we efficiently and effectively maintain these? Simple measurements like that can really go a long way. That data has been used. The data on the project that I was discussing with the large underground infiltration system, we had over 15 years of data on that system, and we were designing a different underground storage area, and that was designed with a header row, knowing, like you said, that multiple levels of treatment, multiple levels of pre-treatment really have a big impact on costs for maintenance. So by putting a header row in, most of these have a header row. I should have explained a header row with a weir as one more location that water can build up, settle out, and be much more easily maintained than having to clean out an entire pipe gallery. So that data that was collected, very simple data, was used to then show, here's an improvement we could make to a system design, which I think is really from a person that has jumped into catch basins and poke down into gross solids. It's really rewarding to know, like, I can take simple measurements that then, when provided to the right group of people, can really take that and use that information to improve a lot of the systems that we're putting in the ground.
I think just one thing to comment about what you said there too is, a simple volume measurement. Yeah, the volume, we've talked about mass and volume, and I think maintenance is almost more concerned about the volume, because when they're hauling this stuff, it's the volume that's going to fill up their haul vehicles, not the mass. So I think that's also something to consider when we're thinking about data or tracking data. Is it the mass that we're interested in, or the volume that's going to be most interesting to the maintenance people or for tracking?
I have a much better appreciation for John's beginning slide with the big gray elephant. It's much bigger in terms of coarse organic matter than we thought, and it also has 4 legs. It's on the move. It's a moving target. I also want to appreciate our time here and that we're a little over. So I'm going to ask our panelists to wrap up our conversations with a lesson learned about what we've heard today. So I'm going to begin down at the far end of the table. Aaron, maybe some final comments or lessons learned for you as you wrap up today.
I think the biggest ones for me would be just how much we might be underestimating, number one. And then we know that, now, but the seasonality of it was maybe the biggest takeaway from me. I also would have thought that fall would have been the highest time or peak loading for coarse organic matter. And it is a little surprising that it's spring, or winter even, but it makes sense with some of those leaves sticking on the trees well into January. Oak trees especially will do that. And all the stuff that accumulates in the snowbank. I think Dwayne calls it SNIRT, snow and dirt, right? Dwayne Stensland at MnDOT. So yeah, I mean, it makes sense that pulse is huge in that winter, that first flush, and I think that was a big takeaway for me.
Thank you. And Paula.
Yeah, I think the snow melt piece was very interesting and kind of added to my feeling that we don't think about snow melt enough with stormwater. It's kind of not stormwater, but we need to, in some conversations, but we need to include it as stormwater. But bigger, more than that, just treatment train, source control, emphasize source control, emphasize pretreatment, don't undersize pretreatment. And I think that we probably have been. So that's mine.
All right. And Sarah.
Yeah, I think I'd piggyback off of that we have really found pretreatment to be successful with planned maintenance. And I think seeing a lot of the presentation really emphasized that for me, that having that plan in place is going to continue to be so important, knowing that this is the research that really proves how much of an impact this has.
Great. And before we get to our final comments from our keynote presenter, a reminder that we will save all our questions for those online and give all our panelists a chance to respond to those and post those following the seminar. And you can check out the recording following today. But final comments from our keynote presenter, Dr. John Chapman, about coarse organic matter and everything we've heard today. Were lessons learned and next steps you think we can go ahead as an industry?
So I think this material is big and the problems are big. And because of that, I think we need a lot of help. We need a lot of people working together. And I think it's the partnerships that I just want to stress as my final statement is, a lot of the data that we had was provided to us. The sites were shared with us. And this is really what helped us to get as far as we did with what we had. And so it's the amount of researchers working on this and sharing their data that's really allowing us to make some progress on this. So I just want to recognize that and thank all of those partners and the the sites that we were able to use and the data that was shared. And that's, I think, partway how we're going to get moving this forward. So thank you.
Well, the story is unfolding on coarse organic matters, and hopefully we can all be a part of that continuing research and work and discoveries. I want to give appreciation to John and all our panelists and a round of applause for all of them, please. Thank you all for joining us. Reminder that our next seminar is February 22. You can check that out online and have yourselves a great day.